Heat exchangers are systems used to transfer heat between a source and a working fluid. The difference in temperature allows heat to transfer from the hotter medium to either cool or heat the working fluid. The simplest type of heat exchanger consists of two concentric pipes of different diameters, called the double pipe heat exchanger. One fluid in a double pipe heat exchanger flows through the smaller pipe, while the other fluid flows through the annulus space between the two pipes. In a double pipe heat exchanger, two types of flow arrangement are possible. In parallel flow, both the hot and cold fluids enter the heat exchanger at the same end and move in the same direction, while in counterflow, the hot and cold fluids enter the heat exchanger at opposite ends and flow in opposite directions. Here we can see another difference between the parallel flow and the counterflow. For the parallel flow, the change in temperature for both fluids can be quite dramatic, while in the counterflow situation, things remain constant. Another type of heat exchanger is the compact heat exchanger, where the two fluids usually move perpendicular to each other, called crossflow. The crossflow is further classified as unmixed and mixed flow depending on the flow configuration. The cross flow is said to be unmixed when the plate fins force the fluid to flow through a particular interfin spacing and prevent it from moving in the transverse direction. The cross flow is said to be mixed when the fluid is free to move in the transverse direction. First thing we can tackle when it comes to heat exchangers is the thermal resistance. A heat exchanger typically involves two flowing fluids separated by a solid wall. Heat is first transferred from the hot fluid to the wall by convection, through the wall by conduction, and from the wall to the cold fluid again by convection. Any radiation effects are usually included in the convection heat transfer coefficients. The thermal resistance network associated with this heat transfer process involves two convection and one conduction resistances. In the analysis of heat exchangers, it is convenient to combine all the thermal resistances in the path of the heat flow from the hot fluid to the cold one into a single resistance, and to express the rate of heat transfer between the two fluids as a single quantity. Here we can see two different formulas to solve for the rate of heat transfer. Although both formula uses the temperature difference between the two fluids, the first formula uses the total thermal resistance that we can solve with the previous equation, or the surface area multiplied to the overall heat transfer. Here you can see the different types of heat exchanger as well as their overall heat transfer, with the highest being the feed water heater and the steam condenser. Here's another way of solving for the rate of heat transfer. This time we're gonna use the mass flow rate and the constant specific heat of the working medium, this time for the cold fluid stream. For the hot fluid stream, we're just gonna flip the outlet and inlet temperature, since the hot fluid stream will be losing temperature in order to heat up the cold fluid stream. For the final formula under the rate of heat transfer, we're going to take a slightly different approach, this time using the rate of evaporation or condensation of the fluid, and then the enthalpy of vaporization of the fluid at the specified temperature or pressure. Note that we won't be using the change in temperature for either of the fluids. Two methods are used in the analysis of heat exchangers. The log mean temperature difference or LMTD method is the method that is best suited to select a heat exchanger that will achieve a specified temperature change in a fluid stream of known mass flow rate. Meanwhile, the effectiveness NTU method is for predicting the outlet temperatures of the hot and cold fluid streams in a specified heat exchangers. Here we have two formulas under the LMTD methods. However, the second formula, we will be using the correction factor and the log mean temperature, this time for a counterflow case. For the first sample problem, we have steam in the condenser of a power plant is to be condensed at a temperature of 30 degrees Celsius with cooling water from a nearby lake, which enters the tubes of the condenser at 14 degrees Celsius and leaves at 22 degrees Celsius. The surface area of the tube is 45 square meters, and the overall heat transfer coefficient is 2100 watts per square meter degree Celsius. Determine the rate of heat transfer inside the condenser and the mass flow rate of the cooling water needed. Here we are provided with a diagram of the whole system. For our first unknown value, we have to find the rate of heat transfer inside the condenser, which pertains to the tubes run with the cooling water. Now, as we can see with our given, we already have the total heat transfer as well as the area of the heat exchanger. Now, what we don't have is the temperature difference between the two fluids. We can easily get this from the log mean temperature difference, which we can easily get since we have the temperature of the inlet and outlet for the cooling water. Now, if we were to get the log mean temperature difference, we're gonna use the temperature of the steam as well as the cooling water. Now, substituting those values into the equation, we get 11.5415633 degrees Celsius, now which we can use to get the rate of heat transfer inside the condenser using, again, the area of the heat exchanger as well as the total heat transfer, leaving us with 1090.677451 kilowatts. Now, in order to get the mass flow rate of the cooling water, we're gonna take a look again up with the formulas of the rate of heat transfer. Now, one of the formulas that we saw used the mass flow rate and the specific heat of the working medium. Now, since we have the temperature of the cooling water as well as the constants when it comes to the specific heat of water, we can use that. However, in order to find the mass flow rate, we're gonna have to find another value for the rate of heat transfer. Now, luckily, we have solved that from the previous equations. Now, substituting the values that we currently have, especially with these specific heat of water at 4.187 kilojoule per kilogram degrees Celsius, and the temperature of the inlet and outlet of our cooling water, as well as the value of heat rate that we solved earlier, we get 32.56 kilogram per second as our mass flow rate of cooling water. For our second sample problem, a counterflow double pipe heat exchanger is to heat water from 20 degrees Celsius to 80 degrees Celsius at the rate of 1.2 kg per second. The heating is to be accomplished by geothermal water available at 160 degrees Celsius at a mass flow rate of 2 kg per second. The inner tube is thin-walled and has a diameter of 1.5 cm. If the overall heat transfer coefficient of the heat exchanger is 640 watts per square meter degrees Celsius, determine the length of the heat exchanger required to achieve the desired heating. Use Cp is equal to 4.31 kilojoule per kilogram degrees Celsius for the geothermal water. Alright, let's take a look first at our required value, which is the length of the heat exchanger. Unfortunately, we don't have a direct formula for that, and looking at our given, we're gonna have to take the long way around this one. Now, first of all, we're gonna have to get the rate of heat exchange for the cold fluid, and then with that, we're gonna get the outlet temperature of the geothermal water, which would give us a way to get the log mean temperature difference, which we can then use with another formula for the heat exchange rate. And then that's how we can get the area of the heat exchanger. Now we're going to use the area in order to determine the length, which we'll show later. Like I have mentioned, we're going to have to go through different formulas in order to get to our required value, which is the length of the heat exchanger. And first of all, we're going to start with the rate of heat transfer using the cooler fluid in this situation, since we already have all the necessary values in order to compute the value. Now, once we have that, we get 301.464 kilowatts after simply substituting our different values. Now, using that rate of heat transfer, we can get the temperature of the geothermal water on the outlet simply by rearranging our values basically in that we get 125.0273782 degrees Celsius, signifying that there is certain amount of heat that's transferred into the cool water between the two fluids. Now, before we proceed with getting the log mean temperature difference, let's take a moment to analyze our current setup for the heat exchanger. This heat exchanger is under a counterflow scenario, meaning that this would be our diagram. Unlike the parallel flow, the temperature for the outlet for both heat exchangers would be on the right side, and then both inlet temperatures would be on the left side. But in this scenario, for the hot fluid, the outlet would still be in the right side. However, for the cold fluid, the inlet temperature would be on the right side instead of left. Now that's what we're gonna use to get the difference of temperature for their outlet, but we're gonna base with the outlet of the hot fluid. Now with that, for the difference temperature, for the first one, we have 80 degrees Celsius using the inlet temperature for the hot fluid and the output temperature for the cold fluid. And then on the next one, we have 105 degrees Celsius. Now using the outlet temperature again for the hot fluid, but with the inlet temperature of the cold fluid. Now substituting those values into our formula for the log mean temperature difference, we get 91.94669 degrees Celsius. All right, we're nearing the end of our computation here, guys. So now let's use our computed value for the rate of heat transfer as well as the log mean temperature difference in order to find the area, which would be easy since we already have the total energy transfer or heat transfer rather for this heat exchanger. Now manipulating our values, we get our area at 5.122941006 square meters. Now, like I said earlier, we're just gonna use the area in order to get the length of our heat exchanger. Now, let's take a look at the shape of our heat exchanger, which is a cylinder basically. So for the area, we're talking about the area on the outside, yes, in the side of the tube, meaning the horizontal length, not including the circles. So that's the value that we have right now. Now, for getting the surface area of our cylinder, normally we would add the area of those two circles you see right there in white. However, we're only going to use the part that is in gray, which would be given by the formula pi dl. Now, we already have the diameter of this um, heat exchanger, but we're going to have to convert it into meters since it's in currently in centimeter simply by dividing it by 100, and then we can plug it in into our formula. Now manipulating the given, we get the length at 108.71 meters. This is the length of the heat exchanger that can achieve our desired heating.
For problem number 1, basahin muna natin yung problem. So, sabi sa problem, what is the log mean temperature difference in degrees Celsius of a double pipe counterflow heat exchanger where a fluid enters 90 degrees Celsius and exits at 50 degrees Celsius. So inside the inner pipe, another fluid enters at 30 degrees Celsius and exits at 60 degrees Celsius. So the first thing na kailangan natin gawin is mag-drawing ng temperature flow diagram. Makikita natin sa screen na nakasulat yung heat and temperature flow na nabanggit sa problem. So yung hot fluid na i-cool down natin is nasa taas since mas mataas yung temperature niya. Then yung pang cool down natin na fluid is nasa baba since mas mababa yung temperature niya. So for log mean temperature difference, what we're going to do is just to get the temperature difference between the two consecutive temperatures. So since counterflow siya, yung ima-minus natin is yung hot fluid sa inlet minus yung cold fluid sa outlet. So that is 90 degrees Celsius minus 60 degrees Celsius. So 30 degrees Celsius yung temperature difference natin sa una. Then sa pangalawa naman, yung hot fluid naman sa outlet minus yung cold fluid sa inlet, which is 50 degrees Celsius minus 30 degrees Celsius. After makuha yung temperature difference, gagamitin lang natin siya sa formula, which is yung temperature difference 1 minus temperature difference 2 all over ln temperature difference 1 all over temperature difference 2. So 30 degrees Celsius minus 20 degrees Celsius all over ln 30 over 20, we will get 24.663 degrees Celsius. Next, for the next problem naman, ito naman dalawa yung hinahanap. So, basahin muna natin yung problem bago natin isolve. A lubricating oil cooler uses counterflow heat exchange with a net heat transfer area of 288 feet squared. Cool 63,000 pound mass of oil per hour from a temperature of 146 degree Fahrenheit at inlet to 116 degree Fahrenheit at discharge. So the temperatures of the cooling water are 75 degree Fahrenheit and 90 degree Fahrenheit respectively. The specific heat of the oil is 0.5 BTU per pound of mass degree Fahrenheit. So calculate the following. A. The value of overall heat transfer coefficient in BTU per hour feet squared degree Fahrenheit. And B. The required area for parallel flow device having the same capacity under identical operating conditions in feet squared. So for this problem, same lang siya sa nauna, but we have to get here the overall heat transfer coefficient. So that is denoted by letter U. U yung symbol niya. So saan natin makukuha yun? Ang gagamitin nating formula dito is Q is equal to U times area times change in temperature. Tapos yung change in temperature dito na tinutukoy is yung log mean difference, temperature difference. Tapos yung area naman is given naman yung area. So ang need lang nating kunin is yung heat in heat exchanger. Tapos yung log mean temperature difference. So yung heat, dito muna tayo sa heat in heat exchanger. Syempre, kailangan nating kunin dito is yung heat sa heat exchanger, hindi nung fluid, kasi yung hinahanap is yung heat transfer coefficient mula dun sa mataas na temperature. So para makuha yun, kunin lang natin yung mass nung lubricating oil Tapos multiply natin siya sa CP, which is given naman 0.5 BTU LBM degree Fahrenheit. Tapos yung temperature difference natin sa heat exchanger or dun sa higher temperature. So substitute the value 63,000 pound mass per hour multiplied by 0.5 BTU per pound mass degree Fahrenheit multiplied by 146 degree Fahrenheit minus 116 degree Fahrenheit. So ang makukuha nating overall heat in heat exchanger is 945,000 BTU per hour. So para naman sa log mean temperature difference, same process ulit ng number 1. So ipagma-minus lang natin yung temperature ng hot fluid sa inlet minus yung temperature ng cold fluid sa outlet. So that is 146 degree Fahrenheit minus 90 degree Fahrenheit. We get 56 degree Fahrenheit. So ang change in temperature natin sa change in temperature 1 is 56 degree Fahrenheit. Tapos sa pangalawa naman, yung kukunin natin yung temperature ng fluid sa outlet, tapos ima-minus natin yon sa temperature ng cold fluid sa inlet, which is 116 degree Fahrenheit minus 75 degree Fahrenheit. Substituting the value, we will get 56 degree Fahrenheit minus 41 degree Fahrenheit all over ln 56 over 41. So, ang makukuha nating temperature, log mean temperature difference is 48.1109 degree Fahrenheit. So, nakuha na natin yung mga need na value sa formula. So, pwede na nating masolve yung U, which is Q all over area times yung log mean temperature difference. So, substituting the formula, we will get 945,000 BTU per hour all over 288 feet squared tas times 48.1109 degree Fahrenheit. So, ang makukuha nating sagot dito is 68.298 BTU per feet squared hour degree Fahrenheit. So, sa number 2 naman, since ang kinukuha sa 1 is value of overall heat coefficient lang ng counterflow, sa pangalawa naman is ang kinukuha na yung area in case na parallel flow naman yung device. So, same conditions daw ulit. So, para dito, gagawa tayo ng panibagong diagram para sa temperature since parallel na siya. So, dito sa pangalawang problem, iba na siya sa nauna since parallel na siya. Ngayon, ang magiging process naman natin dito, di ba kanina, yung inlet natin, minus natin sa outlet, yung outlet temperature ng cold water. Ngayon naman, yung inlet natin ng hot fluid, ima-minus naman natin sa inlet ng cold fluid. So, 146 degree Fahrenheit minus 75 degree Fahrenheit na siya. So, tapos, yung outlet naman, yung outlet ng hot fluid, ima-minus din natin sa outlet temperature ng cold fluid. So, 116 degree Fahrenheit minus 90 degree Fahrenheit. So, makukuha natin dyan is 71 degree Fahrenheit at 26 degree Fahrenheit. So, kailangan natin kunin yung log mean temperature difference kasi ang gagamitin nating formula dito is yung formula ng heat is equal to U, temperature difference times area. So, substituting the values, we will get 71 degree Fahrenheit minus 26 degree Fahrenheit all over ln 71 over 26. So, ang log mean temperature difference natin dito is 44.7947 degree Fahrenheit. Ngayon, since meron na tayong LMTD, makukuha na natin yung area. So, gamit yung mga given kanina, yung Q natin is 945,000 BTU per hour. I-divide lang natin siya sa U, which is 68.2018 BTU feet squared hour degree Fahrenheit, tas multiply natin siya sa LMTD, which is 44.7947 degree Fahrenheit. So, hindi ko lang to na box, pero yung area na makukuha natin is 309.321 feet squared. So, ayun yung mga final answers natin para sa pangalawang problem set.
So mag-solve tayo ng isa pang heat exchanger problem. So a gas turbine plant has an exhaust gas generator na nag-handle ng 1.8 kg per second ng air tsaka ng 1.9 kg per second ng hot exhaust gas. So yung temperature na nag-enter is 598 degrees Celsius at nag-leave ng 305 degrees Celsius. So, sa compressed air naman, nag-enter naman siya ng 240 degrees Celsius. So, for this temperature range, binigay yung specific heat or CP ng exhaust na estimated at 1090 joule kilogram mass per degrees Celsius. So, ang hinahanap natin is energy exchange as heat by the two fluids in kilowatt. Pangalawa is air temperature leaving the generator in degrees Celsius. And yung LMTD, loading temperature difference. So, ano yung natin yung mga given niya. Meron tayong mass ng air, 1.8. Meron tayong mass ng gas, 1.9. Temperature ng air is 598. Temperature ng gas, 305. Tsaka temperature ng air ng in, 240 degrees. Tsaka CP ng gas. So, para makuha yung hinanap is yung Q, energy exchange. So, ito rin gagamitin formula. Then, gagawin natin is substitute lang. Yan. Mass ng air is 1.9. CP is 1090 joule per kilogram mass degree Celsius. Then 598 minus 305 degrees Celsius. So ang masagot dyan is 606803 joule per second or 606.803 kilowatts. And ang pangalawang hinahanap is yung air temperature leaving the generator in terms of degrees Celsius. So, ito yung gagamitin formula. Parang MCP lang din. MCP delta T. So, meron tayong ganun lang din. Since meron na tayong heat, meron tayong Q, pwede natin makuha ang temperature ng air. So, substitute lang din. 606.803 kilowatt is equal to 1.8 times CP ng air is 1.0062 kilojoule per kilogram. Then, the out, ito yung hinahanap natin, minus 240 degrees Celsius. Input lang natin sa calcul. Makuha natin is 575.0356 degrees Celsius. Lastly, is yung LMTD, log mean temperature difference. So, yan lang yung formula. Delta T1 minus delta T2 over ln delta T1 over delta T2. So, substitute lang natin ang mga values. Ayan. 598 minus 575 minus 305 minus 240 all over ln ng 598 minus 575 over 305 minus 240. So, ang final answer natin dyan is 40.4017 degrees Celsius. So, let's take a look on another problem. Same lang din. A gas turbine exhaust Stack cooler drops the temperature from 1040 degree Fahrenheit to 580 degree Fahrenheit. So, the cooling water enters the coil at 60 degrees Fahrenheit, meron tayong T in. And after a counterflow passage, meron tayong temperature na 197 degree Fahrenheit. Meron tayong T out. So, meron tayong CP ng gas, 0.26 BTU per pound degree Fahrenheit. So, yung harap natin dito is quantity of water. Meron tayong mass ng exhaust gas. Then, pangalawang hinahanap is LMTD in degree Fahrenheit. Then lastly, overall heat transfer coefficient. Binibigyan din tayo ng condition na area, which is 2200 square feet. And then, yung CP ng water is 1 BTU per pound degree Fahrenheit. So, i-gather lang natin yung mga given. Mass ng gas, temperature ng gas ng in and out, temperature ng water ng in and out, tsaka CP ng gas. So, para malaman mo natin yung mass ng water, kailangan mo natin makuha yung mass ng gas. Ito. Kailangan mo din makuha yung heat exchange in terms of mass ng gas. So, ito yung formula. Then, substitute lang natin yung formula. 105 times 0.26 CP ng gas times ng 1040 minus 580 degree Fahrenheit. Ang makuha natin dyan ay 12,558 BTU per second. Since meron na tayong heat, pwede natin makuha ang mass ng water. So, gawin natin is substitute lang din ulit. Q 12,558 BTU per second is equal to mass ng water times 1 BTU per pound degree Fahrenheit. 187 minus 60 degree Fahrenheit. Okay. Final answer is 91.6642 pounds per second. Ang pangalawang hinahanap is LMTD, log mean temperature difference. Since given naman lahat ang mga temperature, substitute lang din. 1040 minus 197, 580 minus 60, and ln ng delta T1 tsaka delta T2. Final answer is 668.5458 degree Fahrenheit. Then lastly, ang hinahanap natin is overall heat transfer coefficient in BTU per hour square feet degree Fahrenheit. Ito meron tayong formula. Yan. UA delta T. Since binigay ang area is 2,200 square feet. So, kailangan natin i-derive yung overall heat transfer coefficient. So, derive lang natin. Na-derive natin. So, tapos i-substitute 12,558 BTU per second. Since kailangan natin is dapat naka-R, kaya ko-convert natin yung seconds into R times 3,600 all over 2,200 square feet times 668.5458 degrees Fahrenheit. So the final answer is 30.7375 BTU per hour square feet degree Fahrenheit.